Hello, my name is Benjamin Miller. I'm part of the RESESS program, and I am a student at Tufts University in Boston.
Hello, I'm the other RESESS intern. My name is Velazquez Sanchez, and I just graduated from the University of California State University.
And this summer we worked on this project along with our project mentor, Ellen Alexander. So what we focused on this summer is a geochemical analysis of trace element data, specifically on the reliability of two specific trace element ratios as a use as pseudobarometers. We will go into what that means in a second. First, our objective: to use generalized depleted mantle and slab melts and their resulting trace element compositions to essentially build a empirical correlation between SR over Y, also known as strontium over yttrium, and La over Yb, lanthanum over ytterbium. Basically, by testing this empirical correlation, we want to see whether there exists a way to use it. Recent studies have promoted an empirical correlation between these two trace elements that I just mentioned and initial Mohorovich discontinuity depth. By doing so, people have proclaimed this as a pseudobarometer, which I'll get into later, but have been using it to kind of predict and reconstruct arc depth. We are going to test the reliability of this. Specifically, we are examining variations in these two ratios when exposed to different initial pressure and temperature regimes. We are testing the effect of assimilation on these trace element ratios. And lastly, we are comparing our end compositions to real-world data to see how feasible this is as a method of determination. So just a little bit of info: the trace elements of interest are strontium, right here, yttrium, lanthanum, and ytterbium. It's gonna, please forgive us if we mess up the pronunciation, a little thick.
And before we discuss what are pseudobarometers, I just wanted to explain two different types of crust within the Earth. One is oceanic crust, which ranges between 5 to 7 kilometers, and the other is continental crust, which ranges between 10 and 70 kilometers. And because of that huge variation within continental crust, many researchers have attempted to calculate crustal thickness either within young arcs or in ancient arcs, and is the focus of our study, looking at continental crust thickness within an arc setting. And here's just an illustration of a cross-section of what's going on within oceanic and continental collisions. So within this, you're getting a subduction of the oceanic crust, and within that subduction, as the subducting plate subducts, hydrous minerals within the subducting slab release fluids which produce partial melt within the mantle. This melt then rises into the continental crust, which forms within our arc settings. And this picture is just showing more where these melts occur. As you can see, where there's a huge range in which we get these melts. And because of this, we incorporate within our simulations, where we will explain later on, we do different pressures and temperatures that are normal within these sort of arc settings. And the mantle composition within here would be depleted due to the amount of magmatism that's occurring.
So, as I mentioned earlier, we need to discuss what a pseudobarometer is. First, a general barometer is just any way to test pressure, any way to determine any kind of pressure. Most notably in the geochemical and general geoscience community, a very popular form of barometers are thermobarometers, which use very specific thermodynamic reactions, phase assemblages, and other things like that to effectively build and reconstruct pressure and temperature conditions. It's very reliable, it's been very well tested. However, the drawback of it is quite complex and does require a significant bit of work to make sure that it is correct. Pseudobarometers, however, are, as I mentioned earlier, a recently studied empirical correlation, which means that instead of performing a lot of different reactions and using phase equilibria, it involves simply plugging in a number. It's a formulae that It's effectively, if you plug in an SR over Y or an LA over YB ratio, you get back in turn a initial Mohorovic discontinuity depth. Very simple, significantly more simplified, and very streamlined. However, and other studies have come out recently pointing out there's been a lot of inconsistencies in creating this correlation. There was pointed out a lot of sampling bias in the initial construction, and there have been several studies pointing out that this does not work for several ranges across the world. So what we are going to be doing is investigating this reliability. And just a quick illustration of what I was talking about with the studies. So they point out that there is a clear, this depth indicated on the x-axis is the MOHO depth, and it points out that from Profeta et al. And Farner and Lee, two of the more prominent papers on this matter, promote a pretty clear correlation between these two ratios and the depth.
And here's like the theoretical concept of what's actually going on within these ratios or trace elements. So on the figure on the left shows a much more thinner crust relative to what's seen on the right. And because of this thinner crust, the mantle composition at that level would be more rich in plagioclase or dominated with plagioclase. So as melt forms here, based off of the mineralogy within this mantle section, less strontium would be incorporated into the melt, and same thing would be seen within lanthanum. Less lanthanum would be incorporated to the melt, and as the melt rises, you get these lower ratios, which would signify a thinner crust. And on the figure on the right, as you can see, there's a thicker crust, and due to this thicker crust, the mantle composition is more dominated between garnets, and as partial melting occurs there, you're going to get more strontiums and lanthanums incorporated into the melt. And as that melt rises, you're going to get a higher ratios that are indicative of a thicker crust based off of past studies. So methods that we're trying to use, use a or thermodynamic modeling software called Pele, similar to more popular models called such as MELT. This model was used to form initial melts within the NARC settings. However, within Pele, they're using a more idealized minerals compositions and more ideal solutions or bases. So within this model, we're modeling magma forming within different pressures and temperatures that are associated within ARC settings.
And then the next part of our methods were incorporating the GREM, or the Geological Earth Reference Model database, to essentially construct a generalized depleted mantle and slab to assimilate, and then run through Pele at several different pressure and temperature regimes. This is also where we pulled our data for the mid-crystalline tribolite, which we will go into later.
Oh, this picture is just illustrating where these like natural data were collected. So as you can see, they're collected from active continental arcs and some oceanic arcs. And this is where most of the data is associated with.
So to do our mixing, we first generalized a depleted mantle and generalized a slab. We want this to encapsulate as standardized of a mantle melt as possible, which is why we use this generalized version presented on the GREM. And then we assimilated it with a 2% slab fluid, again, to kind of, as that is the most common occurrence in a magma. This formed our bulk composition that we then inputted into Pele. As mentioned before, we did this both with major and trace element ratios to more accurately simulate this melt. We ran this through Pele, which then generated a surface arc composition for each pressure and temperatures that we went through. We did not do 6,000 of these like Zilli and Michaela. However, we ran through about 150 and then plotted and removed outliers as necessary. So going back a little bit, we converted the dependence on the MOHO depth into pressure as to better reflect our initial data. So this is simply the Profeta et al. And Farner and Lee data that we used earlier, or that we presented earlier, just using the line of best fit and then converted to a dependence on pressure instead. Once we had the data from Pele on all of our different pressures and temperatures, we plotted them. And it performed a least squares regression on both trace element ratios. For SR over Y, we noted a linear was the best fit, or linear regression was the best fit, while an exponential fit was best for LA over YB. This actually backs up what the natural data says. In both of the formulae for the pseudobarometers, SR is a simple linear dependence, while LA over YB actually involves logarithms. So this supports the data. And as you can clearly see, there is a dependency on initial pressure in both of the element ratios. As pressure increases and therefore as depth increases, these ratios do increase, which does promote this idea of pseudobarometers. However, where this comparison falls apart is in the comparison to the actual numbers. When we compare it to the natural data found in several of these papers, which is the red lines on each, they significantly outpace and even our highest modeled data. Nearly 5 times the amount in all cases for the Perfetta et al. Paper, and by that the SR over Y paper, and nearly twice as much for the Farner and Lee. However, as you can clearly see from here, it rises exponentially faster than our modeled data. So effectively what this shows is using our model, we only focused on pressure and temperatures and how that affects the trace element ratios. So therefore, if we are fully encapsulating those two, the effect that those two factors have on both trace element ratios, there have to be other impacting factors. So next, what we did was look into assimilation as a factor.
So we wanted to add another variable to the mix of how these ratios would react with assimilation. So assimilation in this context would just be incorporating another crustal rock into the original magma source and see the effects of different degrees of assimilation. So for our purposes, we did assimilation rates of 5%, 10%, 20%, and 30%. And the rock that we used was a mid-crustal amphibolite, which would be predominantly what we would see within the mid-crust. And the composition of that ratio is that the strontium over Y would be 23.8 and LA over YB would be 5. So some assumptions were done was that the assimilation rate was constant, temperature was constant, and the composition that was assimilated was equally assimilated. So some of the findings that we found here was, yes, within the SR over Y, there was an increase in the ratio, but within LA over YB, there is a decrease in the ratios as more crustal rock was assimilated, which is seen within the purple line. So this shows us that this is very dependent on what the crustal composition of how it affects, but even within the SR over Y, these still don't match to what is seen within the real world data, which leads us to, which we found that we failed to reproduce what is seen within the real world database.
Yes, effectively, since this disparity exists, though in a lesser state, even when we include a very high percentage of assimilation, this implies there has to be other factors that we are not considering that are causing a change in both of these trace element ratios. It's not just pressure, and it's not just pressure and assimilation. There have to be other factors. We didn't speak about this too much, but we noticed that there was even a clear change as we increased or decreased the temperature of the initial melt. While not terribly important to the end results of our data, it does show that there are in fact other factors that just are not being taken into account in pseudobarometers. And this is dangerous because there are several papers out there that have simply taken this as fact and using these proven, while clearly empirical correlations, they are not reliable enough to actively reproduce or reconstruct ancient arcs, and yet they're still in use. Therefore, we conclude that the use of these two elements and the use of pseudobarometers as is not reliable enough for use until further examination into other factors is performed. There is potential, However, as of now, it is simply not reliable enough as a method. We would like to thank the National Science Foundation for their grants. We'd also like to thank UNAVCO, Andrea Ellis, and Ellen Alexander, and everyone who supported us over the course of the summer. Thank you very much. And additional references are available if you would like our manuscripts.